Okay, here we are again with some more stuff about limits. This time using algebra, which by algebra I just mean manipulating variables and expressions and equations and stuff to analyze things that way, instead of with a graph or just plugging things into a calculator. So uh, here's some things to remember from before. First of all, the definition of a continuous function at a value, if you plug in a value of x equals c, is that the limit should exist, and not only that, the limit should be equal to the actual function value. So if I was going to draw a picture of that, it would look like this. That's not a pen. There's a pen. So if you plug in a value of c there, and you get a corresponding value f of c as that y coordinate, then if you also plug in values of x close to c on either side, the corresponding y coordinates need to be getting closer and closer to that same thing as you get closer to plugging in x equals c. And so that's a continuous function. And here's some more stuff about continuous functions that's important. So most combinations of continuous functions are also continuous. So if you add up, you sum two continuous functions, the result is a continuous function. If you multiply, the result is a continuous function. If you do function composition, like plugging one function into another, and also inverses of continuous functions are also continuous. So that makes it easy to find limits like this one, because first of all, x squared plus 5, it's always continuous, and not only is it continuous, it's always positive. And natural log here, the natural log function is always continuous when its input is positive, and that happens here. So that means that this is a composition of two continuous functions. So that is greater or equal to 5 at all times, x squared plus 5. So that means natural log, it's always natural log of 5 or greater. So that's a composition of two continuous functions, and the theorem from before said that function composition gives you another continuous function. And then the cosine function is always continuous too. And so if you plug the output of a continuous function, natural log of all the stuff, into cosine, the result is also continuous. And why does that matter here? Because let's see, because if you want to find the limit is equal to the actual function value. So, because that's the definition of what it means to be continuous in the first place. So in this case, that means the result is just the same as cosine of natural log of 2 squared plus 5. And I don't know how to evaluate that other than to just say that it's equal to cosine of ln of 9. You can evaluate that with a calculator if you want to, but we're not gonna. So let's look at a fraction. So if you have a function divided by another function, such as, I don't know, x plus 2 over x squared minus 1 or something like that. That's only continuous at values of x where f and g, the top and bottom, are both continuous. And that's true of this example I have over here. This is a linear function, it's continuous. The denominator, x squared minus 1, is just a parabola. Quadratic functions are always continuous. So I think I was just bitten by a mosquito while we were recording this video. I think I killed it, maybe. Anyways, but the important thing I was trying to say is the denominator needs to not be 0 for it to be continuous. So this example I have here, it's undefined. The fraction is undefined if x is when x is 1 or -1, which means it can't be continuous, because like to be continuous, f of 1 must exist, and in this case f of 1 is 3 over 0, which is undefined. So so that doesn't work. It's also an asymptote, and the graph is going to make it discontinuous there, so all that stuff. Let's look at this theorem that we had from before, which is that if you take a limit of a fraction function like this, it's equal to the limit of the top over the limit of the bottom if both of those limits exist, and the limit of the top and the limit of the bottom, and the bottom limit is not equal to 0. So that means with something like this other one, if you want to find the limit of this as x approaches, I don't know, 5, this is continuous at x equals 5. So you could just plug in 5 plus 2 over 5 squared minus 1, and it would be 7/24. Because if it's continuous there, you can just plug in the value to find the limit. So when I see you guys tomorrow, I'm going to be all itchy because, you know why? Because I'm outside avoiding the loud family and getting bitten by mosquitoes. Well, let's see. Okay, so how do you approach limits like that? We have these three sort of different cases where either the bottom is not equal to 0, and if the g of c function, the denominator when you plug in your value is not 0, then that means it's a continuous function there, and you're fine. And you just to find the limit of a continuous function, you can just plug in the value, and that is all good. If the denominator is 0 and the numerator is not 0, then the limit can't exist, because you're going to have something like, let's say you want to find the limit as x approaches 0 of 1 over x. As x gets closer to 0, 1 divided by a really small denominator gets bigger and bigger, and so the graph has this asymptote there. And from one side it's approaching infinity, and from the other side it's approaching negative infinity, so the limit does not exist. And let's see, so that's this example here. Well, it just really doesn't exist, not so much the infinity part. And this third one is when both of the top and the bottom are approaching 0. In that case, the limit may or may not exist and could be anything, and this is mostly the interesting one that we're going to focus on. So what we did before is just like a summary of like 1.8 stuff, but now let's look at these interesting 0 over 0 kinds of limits. Okay, so for this first one, you'll notice that A here, I'll just do that one over here, I guess. If you plug in h equals 0, you get 27 minus 27 over 0, which means that it's undefined there, so you know it's not continuous, so you can't just plug in the function value. So let's see what we can do. One thing we can do is multiply 3 plus h times 3 plus h times 3 plus h 3 times, and you may remember the formula for how to do that. If you cube a binomial like this, you end up getting a cubed plus 3a squared b plus 3ab squared plus b cubed. And so in this case, our a is 3 and our b is h, so really, to evaluate this limit, we're going to have 27 plus 9 times 3 times h plus 3 times h squared plus h cubed minus 27, all divided by h. And so you end up with a 27 minus 27, which adds up to 0. And then you notice each of the remaining terms in the top has an h in it, like so. I can hear my neighbors outside taking their trash cans in. I think they all think I'm weird talking about math in my backyard. So now my neighbors think I'm weird, and I'm getting bitten by mosquitoes, so you guys can thank me later. So I'm just going to factor out that h from the top, and it'll look more like 27 plus 9 plus 9h plus h squared is left over after you take that h out, and there's a h in the bottom. You can reduce that fraction. Now, let's think about reducing this fraction a little bit. This is an important concept here, because this factor of h is kind of like what's giving you the 0 over 0 problem. So how can you just cancel out 0 over 0? It's not like 0 divided by 0 is 1. I just want to make that clear, that 0 over 0 is not 1. 0 over 0 is undefined. I don't think I have time to explain that right now. Why is that undefined? So I'm going to refer you to your favorite search engine if you're interested. Anyways, or maybe you already know. Don't Google it if you already know. High five if you already know. That's a good thing to know. Anyways, we reduce these h, or why are we allowed to reduce these h's? This is what I was trying to get to here, is because this fraction here is equal to one of two different things. I'm going to write this fraction on the side. It's equal to, if h is not 0, you can just reduce it. If you're plugging h equals 1 or h equals 5, 5 over 5 is 1, so you can just reduce it. And you get 27 plus 9h plus h squared, if h is not 0. And if h is 0, then the top is 0 and the bottom is 0, and it's undefined. So why are we just allowed to cancel it out? Because we're interested in when h is 0, right? But not really. You know, with limits, the limit is only concerned with values of h close to 0, and not h equals 0 itself. That's important enough. I'm going to write. Okay, so yeah, only values close to h equals 0 determine the limit, not h equals 0 itself. and you can check the definition of the limit if you want to see that. It's a good thing to understand because we're going to be using that a lot. So in this case, this just means that you can cancel that out because it doesn't matter what happens when you plug in h equals 0. So because if you plug in h equals 0.01, then 0.01 over 0.01, that fraction reduces just fine. So this is equal to the limit as h approaches 0 of 27 plus 9h plus h squared. And here you'll notice that as h approaches 0, 9h, 9 times something close to 0 is close to 0. Something close to 0 squared just gets closer to 0. And anyway, this is all a continuous function, so you can just plug in h equals 0 just fine. And the result is 27. By the way, I'll do this sometimes. I like to write this like this sometimes to show that that's approaching 0. Something like that. Anyways, let's do, two more problems. Whoops, I almost forgot. Parts B and C. Okay, B's kind of weird. The thing that's weird about it, that makes this a little difficult, is the square root of x. So we're going to have to deal with that somehow. I'm going to do this one in a green pen because I can. So for B here, to get rid of the square root of x, the trick is to multiply it by the conjugate. So I'll show you what the conjugate of root x minus 2 is. If you do root x minus 2 times root x plus 2, and the idea is to have everything should be the same except for the minus and the plus should be opposites, and then that makes these things conjugates. And the result is x minus 4, because you get root x times root x is x. You have minus 2 root x and plus 2 root x, those cancel out, and then a minus 4. And that's a trick for getting rid of square roots if you want. It also comes in handy with complex numbers and other stuff in other classes. So let's do that. By the way, we only really need to do this if this limit is of the form 0 equals 0. And if you plug in x equals 4, the top and bottom both become 0. So that's why we need to mess around this way. I didn't mention that. So I'm going to multiply the top by the square root of x plus 2 and the bottom by the square root of x plus 2 because it needs to be the same thing. And then this thing happens in the bottom. I don't quite have room there. Where you still have x minus 4 and root x plus 2 in the top. I'll skip multiplying that for now because the bottom is just going to become x minus 4 like we just said there. I just called myself we. I mean the royal we. Anyways, that reduces as long as x is not equal to 4, and again, x equals 4 is irrelevant for limits. And so this result comes out to be the limit as x approaches 4 of, and anyway, square roots are continuous as long as x is positive. I don't know if I mentioned that before, but you know what the graph looks like of a square root function. And then adding 2 doesn't change anything. It just moves the graph up by 2. So the square root of x plus 2 is a continuous function. So you can just plug in x equals 4 into this here, and the function value is the same as the limit because it's continuous, and the answer is 4. Okay, so for part C, this is again the same idea. I'll just do this one really quick. By the way, I keep forgetting to mention this. It's a good idea to pause it for each one of these. Try to do as much as you can, and then press play and see if I did the same thing as you. See if you got the same answer. Maybe you did it a different way. But anyways, you always want to be able to fast forward and go back and check things and pause things and try to be doing as much as you can. So I'm going to do C really quick here. So now's a good time to pause it. And because I'm going to pause it myself too, and in one moment I'll be talking to you in the future. Alright, welcome back. There's my answer. You can pause it and check it. Hopefully you got does not exist. Just doing that every once in a while to speed things along. Ignore this thing over here for now. But what about limits of the form infinity over infinity? Here's what I mean by that. If I were to, let's just look at part A on the side over here, just to think about that. If you take the limit of 3 plus 4y as y approaches infinity here, technically this limit doesn't exist because it is getting closer to infinity. It just gets bigger and bigger in the positive direction. But the limit doesn't exist. You could say one special kind of a limit not existing is if it gets bigger and bigger in the positive direction. You could say y as y approaches infinity, 3 plus 4y is infinity, which technically isn't really a limit, but you know what that means. So that means that the limit of the top doesn't exist and the limit of the bottom doesn't really exist. But what if you just divide them? Is it going to equal something? And you might remember from before that the way we looked at this in 1.8 and 1.9, looking at it from like a graphical perspective or a numerical perspective, is when you plug in big greater values of y here, the 3 starts to get relatively smaller and the 2 is relatively smaller, and you end up getting something pretty close to 4. But anyways, let's just show that it's 4 using some algebra tricks, which will help in some situations. So the trick is to get the limits to not be equal to infinity by multiplying both sides of the fraction by 1 over y. And in general, you want to do 1 over whatever the highest power of y is to make it so the whole thing kind of scales down. And it ends up looking like the limit and at this point, the top is going to get closer and closer to 4 because the 3 over y part, that just gets closer to 0 as y gets closer to infinity. 2 over y also gets closer to 0. So the whole thing ends up just getting closer to 0 plus 4 over 1 plus 0. So, which is also known as 4. And that's another way of looking at it, at problems like this. You can look at this by doing this algebraic trick to show that it's approaching 4 over 1, or just what you know about really big values of y, or maybe with a calculator, or just plugging in big numbers. B is a similar idea here. Let's take this one, and again, the top is approaching infinity and the bottom's approaching infinity. So what can we do? I'm going to try to cancel stuff out to kind of we'll see how it works. And the trick is I see they're both something to the power x. So there's a rule about fractions that if you have like a to the m over b to the m, that's the same thing as just a over b to the m. And just using that general rule of fractions will help us think about this. So I'm going to write this as 2 to the power x times 2. That 2 is just 2 to the 1. So 2 to the x times 2 to the 1 is the same as 2 to the x plus 1. And then I'm going to try to write this as 3 to the x here. And what else do we need? We need 3 to a power to get x minus 1. That can be negative 1. That will be the same thing. So now I'm going to do this trick with fractions to say if they're both to the power x, then this is the same thing as and this is times 2 times 3. And let's think about what will happen with that. So 2/3 to the power x, if x is really big, 2/3 is less than 1. So when you do 2/3 times 2/3 times 2/3 a bunch of times, it just gets smaller the more times you multiply it by itself. So that's going to approach 0. So the whole thing's going to get closer to 0 times 2 times 3, which is 0, is the answer to that. Okay, I'm going to pause it here, and then next we're going to talk about weird limits like this one and the squeeze theorem. Okay, here is round 2 of section 1.9. We just have a couple more things to do, basically one more problem here. This involves a pretty weird function, f of x equals x squared times cosine of 1 over x. Let's see what happens to this as x approaches 0 here. So first, let's look at what does just cosine of 1 over x do by itself. I'm gonna go to desmos.com. I'm going to pause it while it's loading. Okay, so if we're graphing y equals cosine of 1 over x, it has this weird behavior as you get closer to 0, which is the 1 over x part gets closer to infinity, and the bigger that gets, cosine just goes up and down forever. So that happens as x approaches 0 here, which we can see as we zoom in here. The closer you get to 0, I'm just zooming in horizontally here, not even changing the y-axis, but it just keeps coming out. So it goes up and down an infinite number of times in here. I can't really drag it properly anymore, but that's cosine of 1 over x. Now let's look at that and also look at a graph of y equals x squared, the other part of this. Now my window's all messed up. Okay, there's a regular old parabola. So what happens when you multiply the y-coordinates of one times the y-coordinates of the other one? Then, well, as the y-coordinates get closer to 0 and the cosine values always stay between -1 and 1, you're going to get things that go closer to 0. So let's just see what that looks like if I just do that right here. So there is a graph of y equals x squared and y equals cosine, there multiplied by cosine x. And then we can also get a graph of y equals negative x squared here, which looks like that. So for some of the points like here and here and here and here, it looks like that's where cosine is either 1 or negative 1, and multiplying that by x squared just gives you the same thing as x squared or negative x squared. So that's what's happening here, and you can sort of tell that the closer that x gets to 0 here, as you zoom in, what's happening to the y coordinates? They're kind of also getting squeezed in towards 0 as well. So you get that kind of cool graph there. So it looks from the graph like it's 0. But just from thinking about it that way, you can deduce that it's 0. So I guess I don't really have anything left to say here. But maybe one way, I'm going to introduce this next theorem, I guess, which is that what we have here is that the limit as x approaches 0 of x squared is, of course, 0. And the limit as x approaches 0 of negative x squared is also 0. And what we also know is that the x squared times cosine of x is always in between x squared and negative x squared, because cosine of x itself here is always in between negative 1 and 1. And when you multiply x squared times something between negative 1 and 1, you get something between negative x squared and x squared. And so because both of these limits are going to 0 and our function is between, you can see that that makes the graph squeeze the limit in. So we can tell from the graph and this reasoning here that the limit weird. Is 0. Anyways, this is an example of the squeeze theorem. So if you have a function f of x which is in between the output values, y coordinates are in between these other two functions b and a, for all values of x close to x equals c, except possibly at x equals c, and the limit of b of x is equal to L, and the limit of a of x is also equal to L, then f of x is getting squeezed in there towards L2. So in general, you could draw another picture of it that looks like this. I'm going to pause it. All right, so here's my picture of this. So in black is the oh Jesus, I drew them on the wrong side. Okay, let's fix that. So you have some function here in black that is greater than your f of x all the time, and or at least close to that point. Maybe it dips below over here, but that's no problem, doesn't matter. And then your b of x is the one below, and that, you know something about that one. Maybe that's a simpler function, I don't know. But both of these have the same limit here. They're both getting closer and closer to L, and f of x is in between them here. I just realized my function graph fails the vertical line test, so it's not even the graph of a function. So I'm just redrawing the whole thing anyways. Then if it's in between them, then it must have the same limit. And this might happen, and the reason why this is useful is because usually there's simple functions that work as your b of x and your a of x functions, such as like the parabolas we saw before. And then your f of x might be something more complicated that's wiggling around in there in some weird way. Okay, so I need to move the recording window over. Oh, much better. Okay. So let's look at this function. F of x equals, that's our last example. F of x equals 1 over x plus e to the negative x. We want to prove that its limit as x approaches infinity is 0. So we're going to sort of use a version of the squeeze theorem. And you want to think about a function that's kind of similar to this one that we know something about. And so I look at the part of it that's weird, the e to the negative x, and I say, let's ignore the weird part and see what happens if we just have 1 over x. So that limit is, of course, 0, because as the x gets larger, 1 over x gets smaller. But how does the plus e to the negative x change it? Well, remember, first of all, e to the negative x, e to any power is always greater than 0. So what does adding it to the denominator do to the function? Well, if you just make the denominator of a fraction larger, it makes the result smaller. So that's going to make it look like 1 over x plus e to the negative x is smaller than just 1 over x. So that's something we know about it, and we know what this limit does. To make the squeeze theorem work, we need to have another function over here that our function is greater than, that also approaches 0. Because so far we have the upper boundary, you can call it. Oops. The upper boundary here is the a of x part, but what is this other thing below it, the b that is also approaching 0? Well, something that's always greater than this, but whose limit approaches 0 is 0. That works. So both of these things here approach 0. I mean, 0 is already there, so it doesn't even need to approach it. They both approach 0, and this one is squeezed in between them, so by the squeeze theorem, we can conclude that our limit is equal to 0. So that sounds good. Hopefully I had fewer technical difficulties this time. It seems like it went a little bit better. I'll see you in class. And have a good night or day.